Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. After celebrating the completion of our new super duper forward plus lighting system, it's now time to advance to the next topic, which is adding support for textures. In this episode, we'll concentrate on writing the C++ code, which imports images and constructs textures from those images in various shapes and flavors. Before working on importing textures, I'd like to spend a couple of minutes to improve the problem with light sets, which is caused by the fact that light sets are created implicitly when we add the first light that's supposed to go in a specific light set. Therefore, if we never add any lights, we also never create any light sets, while the renderer expects us to provide a light set key, which we obviously don't have. One way of fixing this issue is to make light set creation explicit. That means that we can't add any lights without having created a light set first. Trying to add a light to a non-existent light set will then fail. We'll add two new function pointers to the renderer interface. These can be used to call the low-level renderer functions that create and remove light sets. The user provides a key that's associated with a created light set. The same key can be used to remove the light set. We can call these functions in the high-level renderer using the reference to the low-level renderer interface. We've been using this for all other function pointers, and these ones are no different. We need to implement the low-level functionality next. Before creating a new light set, we assert that it doesn't already exist. Then we add an empty light set with the provided key. When removing a light set, we check if a light set with that key exists and that it has no lights. We expect that all lights in a light set have been removed before calling this function. The light set is removed by calling the erase function, again using the provided light set key. When shutting down the renderer, we don't have to check if all light sets are empty, since that's already done when removing light sets. Instead, we assert that all light sets have been removed. Now, whenever we create a light, we check that a light set exists with the provided key. The assertion will fail otherwise. At the end, we can put back the assertions which we had to comment out previously. And finally, we have to plug the new functions into the renderer interface so the high-level renderer can call them. Obviously, if we try to run it now, we'll get an assertion failure when the first light is being created. So before generating lights, we call the new functions to create the two light sets and remove them when we shut down the application. While we are here, I'd like to increase the light intensity for point lights and spotlights to make them a bit more vibrant. I think right now they're a bit dull. I also fine-tuned the intensity in the test shader. I see that I set the wrong intensity value, and also I made a copy-paste error here. Here we should of course call remove light set instead. And I'll increase the correct light intensity. That looks better. Now if we don't create any light sets at all, we end up with a problem, so we have to create at least one light set, even if we have absolutely no lights in the scene, not even directional lights. Well, I think that's an acceptable requirement. And as expected, it works fine when we do create a light set without any lights. That's all for light sets. Now we can start our new adventure in juggling with textures. Let me close all files and explain how I'd like to set up the texture importing pipeline. At a high level, we start with a list of image files which we would like to import into a texture asset. We'll read and, if necessary, decode these files in memory. Most file formats use some kind of encoding or compression in order to make the file size smaller. After loading the files in memory, we can either save them directly to a texture asset file in raw format, or optionally encode the resulting texture in a block compressed format. These are lossy compression formats that can be decoded on the hardware while the shader is sampling the texture. The advantage of using block compression is that it uses less memory. We'll see how this works in a later video, and I'll also explain those formats in a bit more detail when we are going to use them for our imported textures. If we manage to successfully load all images that we want to use for a texture asset, then we send the data over to the editor, which will save it to an asset file. So this part of the pipeline is in C++, and we are going to use the DirectXTex library for reading and encoding the images. Those of you who have been following this series for some time may already know that in general we like to minimize third-party dependencies in order to maximize the learning experience and also keep the building process of this project as simple as we can. I decided to make an exception in this case because decoding and encoding various image file formats is something that could take a very long time to do correctly, simply because of the sheer number of different formats and edge cases. Even if I would go down that rabbit hole, I'm not sure if I could get any benefits out of it in terms of performance or efficiency. That's why I'm going to use this library, which I think does a very decent job of providing the functionality that we are looking for. It's also open source and offers more than just the functions for image processing. Here you can see the list of various functionality that it offers. However, we are only going to use it for importing textures. Looking at the pipeline in a bit more detail, we see that a list of image files is provided in the import settings data structure, along with other properties which we'd like our texture to have. For example, we could tell the importer to create an array of 2D textures or a 3D volume texture by providing the appropriate setting. Next, we read the image files, which could be in any of these file formats. Depending on the type of texture that we would like to construct, an intermediate texture is created that contains all the data and information about the texture. Then we can optionally create a chain of bitmaps for this texture. We also have the option to encode the final texture in one of the block compressed formats. As I mentioned, we'll support 1D, 2D, and 3D textures, as well as cube maps. In addition, we can create texture arrays for any texture dimension, except for 3D textures. At the end, this data is sent to the editor, which will save it to an asset file. The first thing we are going to do is to add DirectXTex library to the Content Tools project. We can add it as a NuGet package, but of course it's also available as standalone download, either as binary or source code, so that you could include and use it in your project however you desire. Here we have got two packages that we can use. We have got the Desktop 2019 package and the Desktop Windows 10 package, and the difference is that this one supports Windows 10 and 11, while the 2019 package supports Windows 7. Let's install the one for Windows 10 and later, since we are not going to run on Windows 7. So we select this one and click Install. After installation, it's ready for use, at least in theory. However, in our case, we have got a teeny tiny problem, which is caused by us having multiple build configurations. Looking at the contents of the native target file that comes with the NuGet package, we see that it describes which library files should be used with each build configuration. Debug and release build libraries are used with the corresponding build configs. And the way it decides which one to use is in here, where the configuration name is compared to debug and release, and the NuGet configuration variable is set accordingly. This variable is then used as a part of the path to the library files. So the NuGet configuration is debug for debug builds, and it's release if the build config is called profile or release. However, it's also going to use the release build library files if the build config was none of the above. And here is where the problem is. The build config names which we are using are neither debug, release, or profile. So it would always use the release libraries, even if we are building in debug configuration, which would cause a lot of linker errors. Fortunately, the solution is quite simple. We just define the NuGet configuration variable beforehand and set it according to the build config. Then when the target file is injected into our project, the variable is already defined and therefore it won't be set to release. Problem solved. Just save the project and reload in Visual Studio. We start by adding a new CPP file and name it textureimporter.cpp. Here we include tools common as well as the new DirectXTex header files. Now we'll be able to call functions and use data structures from DirectXTex. Since we are calling quite a few of these functions, we can add the using for the DirectX namespace, so we don't have to type that every time. We'll follow the structure of geometry importer tools. So we add a single function which we call to import image files and construct a texture which is given back to the editor. Because the texture can be created using block compressed format, we'll also need a decompression function in order to be able to load the texture when we want to look at it in the editor. Similar to how we passed geometry data between the editor and the content tools DLL, we are going to use a single structure to pass texture data, which we'll call texture data, just to maintain our very creative naming conventions. I'll define this structure next. It has a constant for the maximum number of MIP levels that a texture can have. This also determines the maximum size of a texture which is supported by our engine. Here we are of course talking about textures that are loaded entirely in GPU memory. There are textures that can be partially streamed in and out of memory, the so-called streaming textures, which can be arbitrarily large. However, we are not supporting those just yet. Let me restart this pinnacle of human ingenuity so we can, heaven forbid, get some work done today. Well, even restarting doesn't help nowadays. I saw Jonathan Blow come up with the very apt name of Visual Stupido, and I think I'm going to adopt and stick with that name moving forward. Anyway, the texture data contains a pointer to a block of memory into which we can put the imported texture. The size of this block is passed in subresource size field. If the texture is block compressed, there is no way for the editor to create an icon from it other than pass it back to the decompression function, which is both slow and wastes a lot of memory. So instead, we put the top-level mipmap image in another block of memory before compressing the texture. This pointer will be null if the texture is not block compressed. The texture info field will contain additional information about the imported texture. We'll define this structure in a minute. Finally, the import settings tell the import function exactly how to import and construct the texture. Let's define texture info first. It contains texture width, height, array size, which is also used for texture depth if we are creating a 3D texture, the number of mipmap levels, and the format of the created texture. It also contains the error code if importing or constructing the texture wasn't successful. Finally, it contains some flags that carry more info about the texture. We'll define the error codes and flags in a bit, after we add the texture import settings. The import settings contain one or more file paths in a single C string. The paths are separated by a semicolon. We'll have to split this C string in an array of strings which point to one or more image files to be imported. As a check, we passed the number of files in another field. The dimension determines if the texture is going to be one-dimensional, 2D, 3D, or a cube map. The desired number of MIP levels is given in the next field. If we pass 0, the full chain of MIP levels will be generated. Next, we have the array size, but I'm not sure if we'll actually use this, since we don't know beforehand how many source images we'll end up having. Remember that some files could contain multiple images. The alpha threshold is only used for low-quality block-compressed color textures with alpha. I'll explain more about block-compressed formats when we write the code that uses the compression function from DirectXTex library. We can indicate if BC7 is to be preferred when we let the texture importer to decide which format to use. If we want to use a specific output format, we can specify that as well. The last one indicates whether we want to use block compression or not. Now let's define an enumeration for texture dimension, which, as I mentioned, is the dimensionality of the texture. Next are the import error codes. Well, I think the error names speak for themselves here. The last enumeration is for imported texture flags. We are going to use this in the engine as well. Therefore, I'm going to put this one in content to engine header file. Here we can define any flags that indicate whether a certain property is present. Again, the names are self-explanatory, but they'll also become more clear once we see how and where they are used. We are now ready to start writing the import function. First, we get a reference to the import settings and check if we have a valid source string. We'll need a scratch image for each file. This is, as the name indicates, a temporary data structure that holds image data and contains every bit of information that belongs to this image. It also has some functions for initialization with or without any image data. In addition, we are going to need a list of images within these scratch images. Remember that each scratch image can have one or more images, whereas the list of images is just a flat list of all images. We are also going to remember the width, height, and the format of the first imported image so that we can check if any of the images that may follow have a different size or format, in which case we return with an error code. Next, we split the file paths. We need to write a function that does that. I'll put it in tools common header so that it can be called from everywhere when needed. So here we have a function that takes a string and a delimiter character and returns a list of strings that contain one or more strings depending on how many delimiter characters were encountered. It's a fairly simple function. It searches the string for the delimiter character from a start position. When such a character is found, it takes the substring from the start till the position where the delimiter was found and adds it to the list of substrings. The start position is then updated to the position past the delimiter. This is repeated until no more delimiter characters are found. In that case, the rest of the string is added to the list of strings, which is returned at the end. Now that we have a split function, we can use it and check if the number of returned strings is the same as the number of image sources. The next step is to load each file into the memory. We'll write a function that takes a file path and returns a scratch image that contains the loaded images. We check if the file exists before trying to read its content. For this, I'll add another small function to tools common header. We can use a Win32 API function to test if a file exists and is not a directory. Here we call getFileAttributes, and if it returns invalid file attributes or it has the directory flag, then we know that we can't use this file. If a file doesn't exist, we set the error code to file not found and then we return an empty scratch image. Actually, let me put all of this together. Okay, so if the file does exist, we can try and load it. We set the error code to load and clear it if we manage to successfully load the file. We are going to read the file assuming it's in a format that's supported by Windows Imaging Component, or WIC for short. Therefore, we can set certain flags when necessary, as we'll see in a minute. For TGA files, we can set TGA flags. For example, if we are going to output one-channel grayscale or two-channel block compressed formats, then we are going to ignore sRGB. For those of you who aren't sure what sRGB means, I'm going to explain sRGB colors in one of the upcoming videos. However, feel free to read this excellent blog about sRGB colors, written by Tom Forsyth, who has got quite a reputation in the world of computer graphics. The loading function of DirectXTex expects the file path string to be in white character format, so we need to convert the path string to W string. Again, I'm going to add this where it can be reused. Here we create a regular string from our C string, and then create a W string from the regular string. Then we get a pointer to the 0 terminated void string, which we can pass to the loading functions. First, we try one of the Wig formats. We can call load from Wig file with the file name, Wig flags, and the scratch image where the image will be loaded into. The function will return an H result to indicate success or failure. If it failed, we try loading the file as TGA. If it couldn't be loaded again, we can try HDR format. If it was indeed an HDR image, we set the isHDR flag in the texture info. In order to be able to use the texture flags, we have to include content to engine header, which contains the flags enumeration. Finally, if it wasn't an HDR image either, we can try and load it as DDS. In that case, we need to decompress it. So we set the error code to decompress and call the decompress function from DirectXTex library. It will decompress all images in the DDS file into the MIP scratch image. If this was successful, we move MIP scratch into our working scratch. At the end, if the HR variable indicates success, we can clear the error code and return the scratch image. Let me also rename this to succeeded. So to recap, we check if the file exists, then set the relevant flags and try to load the file as different formats until we succeed or run out of file formats to try. In that case, the error code contains the value indicating what went wrong. If the error code is non-zero after calling this function, we return. I'd like to stop here for today since the video is getting too long. Next time, we are going to continue with initializing a scratch image with the loaded images according to import settings. We are also going to generate MIP maps for the loaded images. As always, thank you for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!